Hello everyone, welcome to Discrete Mathematics, and today we will talk about graph, and we start with the first part, definition. So we start with some acknowledgements here with the source that I use for the slides. Alright, so graph is a mathematical structure that appears in many applications. So I'll give you three examples here. In this example, we see a graph obtained from social networks. So this graph captures the friendship relationships, of the friendship between persons. For example, between Anto here and Benny here, or between well, Indy here and Lina here. So friendship between those pairs of people. And because the friendship relation here is assumed to be symmetric, then the graph uses undirected edge. So there is an edge between Anto and Benny, and this is not directed. So there is no direction in the edge, and this edge represents the friendship between Anto and Benny. Um, Other examples in social networks include influence graphs, which is you, which is most likely directed ones, as well as collaboration graphs, which will be undirected. I give you two URLs that you could play around, and these URLs uses collaboration graphs behind it. Now for the second example, this is something you see in software design. Uh, we saw here a graph called precedence graph. So a precedence graph captures the relationship between statements in the program, so in computer program. So the idea here is that the statement that precedes another means that that statement has to be executed before the second one. So for example, S1 here precedes S4, as well as S2 precedes S4, and this implies that, or this represents the idea that S1 must and S2 must be executed before we can execute S4. Now the reason is, you see here S1 is and S2 S1 and S2 assign values to the variables x and y, and then S4 uses these values of x and y to obtain the value of w. So therefore S1 and S2 must precede S4. Similarly, S2 must precede S3, because in S3 the value of variable y is used, and in S2 we assign the value to y. But for S3 we don't need S1, because S3 doesn't use variable x. Other examples in software design include module dependency, so dependency between different modules in a software, or function calls, for example, which function calls which function, and so on, and data flow, so how data flows from one process to another. Now for the third example, we see this example in biology. In this particular example, we see a graph representing protein interaction. So we have nine proteins with their own names here, their own codes, and the interaction between these proteins are represented by an edge in this graph. So for example, RRP43 and RRP42 are two proteins that interact. So if you put them together, there will be interactions, and we capture this relation using an edge between these two proteins. So this allows us to understand, for example, which proteins is mostly which proteins has the most influence to other proteins. For example, here you see RRP41 uh, interacts with or has interaction with 1, 2, 3, 4, 5, 6, 7, 8 uh, no 1, 2, 3, 4, yeah, so it has interaction with 8 other proteins, so it is the most influential. Other examples in biology include a graph representing food resource overlap between species. So given in an area or region, there may be many species living in it, and uh, there may be competition between these species because they share the same diet. Or genetic ancestry. So for example, in biology, people uh, say that many reptiles uh, are descendants of dinosaurs, for example, and this is represented by the genetic ancestry. So the dinosaurs are the ancestor of reptiles, for example. Um, and then food chain graph. So the which species is a predator of another species. So those three examples or exhibits uh, tells us that the that graphs as a model, as a mathematical model, appears in a lot of places. Now, but we haven't seen the definition of graph, so we'll see that now, right? So what is graph more exactly? So in exhibit 2, we saw a graph with directions. So we define a directed graph to be to consist of nodes. So phi is the set of nodes, and then edges, e set of edges. So you have a set of nodes and a set of edges, and we assume that uh, there is at least one node in the graph, and then to represent the direction, we use two functions, s and t. So s is called the source function. So given an edge e, s gives us the source. So essentially here, like this. Yeah. So if this is e and this is u and this is phi, then the source of e is u. Right. Now the other function is t, which we call the target function, and the target function maps an edge to a, a target node, yeah, to a target node, te. So for example, here the target of e is phi, right? So let me just slightly make it a full screen. Right. So we saw this as this definition of a directed graph. So it consists of nodes, edges, and the source and target function. And given an edge, its source and target are called its endpoints. And we also say that each edge connects both its endpoints or connects its source to its target. Sometimes the source and target is obvious, so we simply write the graph as its set of nodes and edges. The other type of graph that we saw in exhibit 1 and exhibit 3 is undirected graph. In principle, undirected graphs could be seen as directed graphs, but the edges point to both directions. So in directed graphs, you have one edge goes from one node to another node, but here in undirected graphs, the edges goes from one node to another node and vice versa. So one edge represents both directions. So therefore, we define an undirected graph to consist of nodes, so a set of nodes and a set of edges, and then a function st which gives us the endpoints of an edge. So given an edge, the endpoints would be the endpoints of e would be st of e. So for example, if you have this is u, this is phi, and this is the edge e, then st of e is the set u comma phi. So the set containing these two. Remember, this is a set, so because there is no direction, right? Now, if we don't care about st, or if st is obvious, then we could simply write the pair a graph as a pair of a set of vertex or a set of nodes and a set of edges. Sometimes, of course, u and phi could be equal. So if you have something like this, then st of e would be u. So the set containing just u, right? So we will see the name of this later. So before we see examples, let's remark on some basic terminologies we use in graph. First, a graph may be infinite if the set of nodes or the set of edges are infinite or is infinite. So if any of these two is infinite, then the graph becomes infinite graph. Otherwise, we say the graph is finite. Most of the time in this chapter, we look at finite graphs. And the order of a graph is the cardinality of the set of nodes. So the number of nodes that the graph contains. That will be the order of the graph. And then in a directed graph, each edge has a direction. So therefore, from its source to its target, so therefore we call such an edge a directed graph, and we draw it as a unidirectional arrow. In undirected graph, an edge does not have a source nor a target. So, but we simply have two endpoints for this edge, which may even be the same node. Therefore, we call such an edge undirected edge. So there is no edge, and we simply draw such an edge as a line segment or a curve that connects both its endpoints. Now, an edge is called a loop if it goes from one node to itself. So if it is a directed edge, it will look like this. Yeah, this is E, and here in this case, SE is the same as T of E, which is U. So the source of E is the same as its target, which is U. For undirected edge, it will look like this, and here ST of E is simply contains a single node U. Sometimes also two edges can be parallel. In the case of directed edges, a parallel edge looks like this. This is U, it goes to phi like this, and this is E1 and this is E2, and S of E1 is the same as S of E2, and this is U, and then of course T of E1 is the same of ST of E2, which is phi. So that is for directed edges. For undirected edges, it will look like this. And here, this is E1 and this is E2. ST of E1 is equal to ST of E2, which is the same set, UP. Right. So that's the some parallel edges. So there can be more than two, of course, right? So because you could have more than You could have 3 or 4 parallel edges. A graph without parallel edges and no loop, without parallel edges and without loops, is called simple graph. So simple means there is no parallel edges, there are no parallel edges and there are no loops. And then if a graph may contain or is allowed to contain parallel edges, then we call the graph a multigraph. Sometimes we call it multigraph. And um, such a graph uh, may or may not contain parallel edges. Of course, that means every simple graph is a multigraph without parallel edges. All right, so those are the terminologies. Now let's see examples. Here's an example of undirected graph. This undirected graph has 4 nodes or vertices: A, B, C, and D. So 4 vertices. So therefore, the order of G is 4. And it has 9 edges, which I label E1, E2, E3 up to E9. And because this is undirected, so we have a function st, and st of E1 is the set containing just A. St of E2 is the same as st of E3, which contains A and B. St of E4 contains A and C. St of E5 is the same as St of E6, which contains B and D. And then St of E7 is the same as St of E8, which is the set containing C and D. And then finally, St of E9 contains a single node D. Now you see from the definition of the function st as well as from the pictures, you see that E2 and E3 are parallel, E5 and E6 are parallel, as well as E7 and E8. And finally, also E1 and E9 are loops. That's an example of undirected graph. Another example is directed graph here. Here in this directed graph, which we draw here, by the way, it doesn't matter how we draw it as long as the relationship are correct. So here in this case, we have 6 nodes: A, B, C, D, E, and F, and 10 edges: E1, E2, E3, E4, E5, E6, E7, E8, E9, and E10. Now, because this is directed graph, we will have source and target. The source of E1 is A, the source of E2 is C, the same as the source of E3 and E4, whereas the source of E5 is D, and so on. Now, the target of E1 is B, the target of E2 is B, so they are the same, and so on. So you could have this, right? You could have then you define this for all 10 edges. Now, so you see, for example, E8 and E9 are parallel because source of E8 is B, the same as source of E9, and then the source of E8 and target of E8 and E9 are also E, is also E. So therefore, E8 and E9 are parallel. Notice that E4 and E5 are not parallel because their source and target are different, although they connect. So they make the same nodes be connected, but here in this case they are not parallel because they have different source and target. Also notice that E3 and E7 are loops because the source and the target of those edges are the same. So SE3 is the same as TE3, which is C, yeah. As also SE7 is the same as TE7, which is E, right? So therefore they both of them is or are loops. And also notice that we have a node F here, which is not connected to any other nodes, and this is fine in a graph, so it is possible to have such a node. Now, so let's do some exercise. So we have, you're given, you are asked to define a graph, define two graphs actually. The first one it represents connection between provinces in Sumatra Island, the island of Sumatra. The edge share mean represents the land border, and then a graph, another graph that represents connections between bit strings of length 2. Yeah. Uh, so 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 that here bit string A is connected to bit string B if B can be obtained from A by adding a single bit at the end, so at the rightmost position, and then delete the first bit. So for example, from 00 you could get 01 because you could add 1 at the end and then you delete uh, the first bit, so you get this, right? Right, so do this exercise and we'll discuss the solution in the next video.